Good morning all. Today we're gonna discuss the problem, the color mapping problem in a Prolog language, programming language. Prolog is a logic programming language basically, which is used to write first order logic languages programs. Now I'm gonna start by mapping this problem. First of all, I'm gonna map all the facts that are present in the problem by starting with these predicate. We call these predicates, and we can model all the features, all the regions, the names of the regions, as a list of these values. Now these values in Prolog are just names. It's similar to what we write if we write like this. It's like a string of, like a list of strings. It's very similar. But we write like this with lowercase letters. So we have Western Australia. We have the regions of Western Australia, Northern Territory, Southern Australia, Kiwi Queens, and so on and so forth. Then, and these are called variables, basically. Then we have these domain, which are all the values that we can assign to each of these, the possible values that we can assign to each of these values. So in the case of Western Australia, we can assign red, green, and blue. In the case of North Territory, we can assign also red, green, and blue, and so on and so forth. Then we write some facts, relational facts, about two regions. These are mostly called the constraints. And we have that the Western Australia is adjacent. This is a predicate for adjacent to North Territory. So here we are mapping all the regions that are basically adjacent to each other. So Western Australia to North Territory, Western Australia to Southern Australia, North Territory to Southern Australia, and so on and so forth, all of them. Now we will see that why we are not mapping, later on we'll see that why we are not mapping both ways, like also North Territory and Western Australia. We'll see later on why we are not doing that, because this will be covered in the code part. Like the Prolog code will be able to do this thing. Now after doing this, when we write a Prolog program, first we start by thinking which is the thing that we want to obtain by solving the problem, like which is our expected output. In our case, we can write a query like this: CSP, which is a constraint satisfaction problem, with a solution variable. So basically what we are saying is that we will need some solution. Now what will be the way, or like what will be the type of this solution, for example a list of lists and so on and so forth, we will see later on. But this we know, we will see that it will be a list. In my case, like how I am modeling, there are different ways to model it, but in this case that I'm considering, this will be a list of lists, where the inside lists are referred to each of these domains, domain values. So think about this one. Think about like each list is like a container, all painted in red, the second painted in green, and the third painted in blue. And in each of these containers, we will add these values, the regions. Now, what is the difference between containers is that we cannot add within the same container, red for example, two regions that are adjacent to each other, because this will mean that we will assign, or we will paint the Western Australia and North Territory both with red. But in this problem, the constraint is that you have to paint all the regions in such a way that the adjacent colors are different. So these two has to have different colors, these two different colors, these two different colors, so on and so forth. Now let's begin with the solution. We always keep in mind that we will always start like this. We start from the entry point, but all the things, being that the Prolog is a program that runs from top to bottom, it will go on all these facts here one by one. And when we write the program, we can write it bottom up, but all the values, all the procedures will be added before the entry point, because the running is better. Being that it will, like in Python, the interpreter, basically, it will interpret all the codes one after another, like all the line of codes. Now let's start from the beginning. Now we had CSP. This is just a name. We can put whatever name we want. We can put, but just keep in mind that it has to be in lowercase. So the name has to be in lowercase, basically. And we are in this case is just I've chosen CSP, and this is the solution that I will want to obtain later on. Now what we do is that we start. Firstly, we will start by just mapping or unifying. It's called in Prolog. It's called in first order logic. These predicate with this one. What we will do is that we want to assign this list of values to this variable. Now keep in mind that in Prolog, the uppercase variables, the uppercase letters or uppercase words are called variables, and the lowercase, as I said before, are just values. Now here I will unify. By doing this, I'm saying CSP solution if this is what's called for if. This is a symbol for if, and this is a region to regions, and it will unify here. Then this is an and I'm saying, okay, do this, perform this, and now get me the colors too. So he will also unify the colors by doing this thing, colors and colors in uppercase, and it will unify with this list. So these two now regions and colors, it will be assigned the both lists. Now if you want to see this thing in action, we can also do that basically. So here is group list, and here we can put regions and colors, and you will see that unification works. Now let me put just 2 letters for the query. Colors. And you will see that you'll get, okay, I get this error of singleton variable, but nothing important. And you will see that I have the C variable as unified with the list of colors, and the R value as unified with a list of all values, basically regions. Now going forward, we have that, as I said before, I'm modeling this. In this case, I'm modeling the solution as a list of lists. So what I'm gonna do, I'm gonna pass these colors, this list now, this function which I have created. I will create now. And the job of this one is to count all the elements that are present in the list. And I have the output number of elements. Now I've written it before, and this is the procedure to count the elements. Basically what it does is that this has we basically give an input the colors, and which will enter basically, and this will try to unify with some rules, head of the rule. These are called head of the rules that are previously written. In this case, he will try to unify with this one, but being that colors is not empty, as we saw before, but it has these values. Now it will go further, and it will try to basically unify with this one. Now, does it unify with this one? Yes, because colors, what we are doing here, we know that colors is a list, and in Prolog we can divide this like this, by basically taking the head and taking the tail. The tail will contain the head. It will contain only red in our case, and the tail it will contain green and blue. Now, and C now here is a variable which is basically which at the end it will contain the value that will be assigned to this one. We know that in Prolog the unification is positional. So when we write this type of calling, let's say it, when basically we call the function in this way, what we are doing is that we are mapping this one to this one, and this number n of elements, or number of elements present in the list, with this C variable here. And we move forward on creating this. It's called the procedure. And what we have to do, we have to perform a recursion. Why do we have to perform a recursion? Because we have to meet somehow this stopping condition for this procedure. How do we meet this one? By removing one by one the values that are present in this list of colors. And by removing them one by one, then we will basically count them one by one until we reach the stopping, until we basically finish with elements. Now we start from this. We have divided this in head and tail, but we don't really want head. We just want that, as I said before, we want to reduce the list. So the tail is the list, this list, but reduced with only 2 elements, the 2 remaining ones. So we will go and pass to the same function, count elements, the same. We will pass the T, which is only the tail, so the list of tail, which basically is green and blue, and a variable C1, which is basically just a variable, just to contain the value at the end. It enters here, and what it does, the program, it will go directly here. Try to unify with this one. It sees that it doesn't unify because this is not empty again, and it will go further on unifying with this one. Now what happens here is that we enter here, and this will be divided again in, let's say, HT and TT, basically. So now HT, it will have green, and T, it will have only blue. And C is just a variable, which is unify with C1. Going further, we do again, in recursion, we run again the count element. In this case, only with the tail again. The tail in this case, it will contain only blue, and so on and so forth. It will try to unify with this one. It fails, and it goes to this one, and then do again this one until. And in this step, in the third step, after third steps, basically in the third step, we will have this T, which is, this will be the head blue, and the T, it will be an empty list. Now at this point, this will be empty and this will be some value, some variable. And what it does is that it will unify with this one, because the empty list unified with empty list, and the variable, to the variable c1, it will be assigned 0. Now what happens is that and this cut here, this symbol here, cut, it's called, what it does is that it's saying, once you have unified with this one and this one has gone, like is successful, don't move forward in basically unifying with other functions or with other predicates, because you have finished. Just return your value, and it returns the value to the c1. So c1 now, not let's suppose, but it's 0, and 0 here, this now, we are going back in the recursion, and this now it will have 0 value for the first case. 0 plus 1, it will be assigned 1 to this one, and this will have value 1. Now this will go back as if it was this again. So here we will have two empty lists, a 1, which will go then 1 by 1 plus 1, it will be 2, and 2 it will be assigned somehow here, and then go back until we basically get out of it. And you'll see that at the end it has counted all the values that are present in the list, and this, it will return the c value, which is 3. In our case it's 3. Now why did I put like this? Why did I remove head? Because we are not using head. And when you don't use head when you don't use one variable in Prolog, you can put this placeholder here instead of head, because the main purpose of this is just to reduce the list. It was not to use the head. Moving forward, what we want to do now is that of creating the empty list of lists. But how do we do that? Using this rule which is also created from scratch, basically, which takes in input the number of elements, and it outputs the groups of lists, basically. I have called it groups, so you can call it whatever you want. All these variables are just variables. You can put whatever name you want. Doesn't matter. In my case, I put group list because it's more user-friendly. Like it's more common to do like this. Now, what we have to do, we have to create these list of 3 containers. Here, red, green, blue. How do we do that? We now know the number of elements of the colors, of basically the domains. So we have we have domain with cardinality of 3. So in each of these domains, we will assign the regions. Now, to create this one, it's similar to the count process, but now the difference is that we have a variable that we have to basically decrease each time that we perform some action. Why can we do this one here? Because here we have the value n, it's given, its number of elements. In our case, it would be 3. But here we don't have any value, we have just variables. So this one has to wait to be assigned to this one, for this one then to be used here after this. So it will move on recursion until it gets to this value. When it gets to this value, then it will proceed with this rule, here, basically, with this part of the body of the procedure. Now, same thing here, more or less. But what we do here is that we have to decrease the value, and we assign it to this new variable. You cannot do in Prolog that this will be assigned to n again, because it is an error. It gives an error. We have to assign to another variable and then put the value and call it recursively this one, and now it has a value of 2. In our case, this was 3 minus 1, 2. So 2 with the t. T is just some tail. And here, if you see, we have put the empty list before, and this is called, we just added, basically it's called adding an empty list to the list. And the t-list is just something, it's just a placeholder. And we pass the placeholder here, and we run it again. It tries to unify with this one, and it doesn't succeed because this is not 0, it's a 2. And it goes here again and again and again and again until it meets this condition. So until n1 it has become 0. When it becomes 0, the t it will be assigned this one. And going back, then we will have these results here, like a list of lists. Moving forward now, we can try to solve the problem. How can we do that? We just create a function that we call assign all. In the assign all, you can call it whatever you want. In the assign all, what we want to do is that we want to assign to each of these lists the correct variables, so satisfying the constraints, basically. So the correct one of the variables here, not one but more variables. So each of them will have a different number of, let's say, regions, not variables. And in order to do that, what we have to give this in input to this function is that we have to give all the regions. Which are the regions that we have to assign? We have to give also the groups list that we have created, and also at the end, what we want is that we want the solution to be returned. And this is, now we have to define this procedure here, assign all. First of all, what we have to keep in mind is that we have always a base case, or something called as stopping condition for these procedures. And this is the base case. And then we have an intermediate case, which is all the logic of the program, of the function, basically. In this case, the assignment. Now, what this does, assign all, it will go through all the regions one by one. So we know that these regions here have it's a list. It's this one. We have seen it before. So now what we want is just that we want one value of all of these. How to get one value in Prolog? We do it like this. We just destructure the list, basically. Here we put the head, and in this case we call it better with R, which means region. We put a bar, and then here we have the tail, which to be more basically understandable, we just say that these are other regions that are present in this. So R, it will have Western Australia, and the other regions, it will be a list with all these values here. And this will be destructured here. So when the program sees this one, it will see this one. It will pass this one, because we will see later on what it will have here, because here basically it's a stopping condition. Being that this is a stopping condition, when it is this is met when the other regions have been assigned. So basically the stopping condition, it will have empty list to be basically unified to meet this condition, So we know that this is not empty, and it will go further of this, and it will enter here, basically. Then, as a second value, we have the graph of lists, which is a list of lists. And here, in this case, this function, we don't want to destructure it, because we want all the lists together, in this case. Because it will have another function, which will destructure all the lists. In this case, here, in this procedure, we want just to destructure to go through each of these elements one by one. So destructuring the regions. Now we can pass this one as group lists directly, or we can give it another name, which is basically generally done as current assignments, basically. So which are my current assignments? Or temporary solution. We can also say it like that. And at the end, we will have some output. Here will be some output, but I will explain later. Now let's define this procedure. This procedure has another procedure inside, which will go through these lists one by one. Why? Because if this one, for example, if you want to assign some value here, and this has already, for example, if this first list has the Western Australia, and now we want to assign a Northern Territory, we cannot assign to this Northern Territory to the first list because it will go in conflict with the condition. So we will have to assign it here. In order to pass from this one to go for basically to move on from one list to another, we will have this new condition here, which we call it assign, or we can call it whatever it wants. And the assign, it will have some other values, and then after we finish with assign, we just call it this assign all recursively to move, as I said before, to move on the entire list here one by one. Now, what will have assign inside? Like, what will be the parameters of input of assign? It will be the region, because now assign doesn't care about regions. He cares just about moving on in the list. So you will have a region established by this one. So just put the region, not other regions. And it will need the current assignment. So basically the list of lists, as we call it, or group of lists. And you'll give in return a temporary solution. We can just call it temporary solution. This solution is just, it will be a list, this list of lists, but with one variable assigned, which is b, or more variables assigned. In this case, it will be just one with a r assigned to one of these, satisfying the conditions. Then we'll move forward to calling it recursively. And assign all is just this one. But now, if this succeeded, assign, what we have to do is that we have to move on. We have to select one of these now, because this one was assigned. So what we pass here is that we will pass the other regions. As the current assignment, it will be the temporary solution, because now the current assignment has basically has been changed by this one. Because this one, it will be the empty list, the list of lists all empty. Now this one is like we can call it, maybe it's better to call it current assignment 2. Generally more used like this. It's like current assignment modified. And then we have the solution, basically, which will have it also here. This will basically be the solution of the whole problem. And then we can close this. Now the stopping condition is that this has to be empty, and this current assignment, and here you have the solution. But in order for the solution to have some values, to have the values, because solution doesn't have anything, this will be, when we have nothing left, this should basically, this function here, this procedure, it will be his job to assign this variable here to some values, or the solution, basically. So the solution, it will be equal to current assignments. Now you can say why I'm writing current assignments and not current assignments too. In reality, it doesn't matter because the unification is positional. So at the end, this value that is in the middle, it will be unified with this one. It doesn't care the name. And now if to write it in an implicit way, which is better in Prolog, it's like current assignment here, 2, for example, it will be directly, we can put solution here directly, and it will basically it will be mapped based on position. And here we have to put the cut in order to say that these are mutually exclusive. So once we meet this condition, you don't enter here. And this is the first condition here, the first procedure. Now, moving forward, we have to basically create this assign here procedure, which is another procedure. And as I said before, it has to go basically it will require moving along this list now. So what we have to do is that we have to first see which is the region. So regions, we can just call it again region with R, but as it belongs to current assignments, we have to destructure it. It's not called destructure, but I call it like this. And this, we can call it the first group, or the first list, and the other lists, other groups, basically. And here will be the output, then we'll discuss what will be. Then let's define this one. What this assign has to do is that it has to the first case, okay, here we have two cases. First case one is when the constraint is satisfied. So what happens if the constraint is satisfied? Constraint is satisfied. What does it mean? It means that even when we basically assign this R to this one, the constraint has to be satisfied. If it's not satisfied, it will enter here, and this will produce false. So it will go out and enter in the next part of the procedure, basically. So what it should satisfy is that constraint, which will be defined now. Constraint which gets in input. What we'll have to do here with this constraint function or procedure also is that we have to verify that this region is not adjacent to all the other values. In the group, we have to see. We basically have to create this procedure that checks if this region is not adjacent to any of the values that are present in one of these. In this case, it will be the first one, then the second, then the third, and so on and so forth. So if this is true, what will happen is that we have to return something. So what can we return? What we have to return? We have to return the assignment of R to this G, which is a list. So how does the assignment in Prolog happens? By doing R line G. So here we are assigning to this list basically in the head we are putting the region. In the first case it would be Western Australia. So R is Western Australia assigned to the G, which is empty. And then we have to return also the other lists that are here, because we have also these lists. So in order to return them, we have just modified this one, and we have to return, which is the head. This is the head of all the other in this list. In this list here, this one is the head, the first one. And then we have all the OG are all these lists. all these two, and then we put the list again, and this is the output that will be returned basically from this one. Now this is the first case. Which is the second case? The second case is when basically the second case is when the constraint is not satisfied. Constraint is not satisfied. What happens in this case is that we will have to go further in the other lists. So we have to move forward in assigning this value R to another list, because we assume that if we leave the function, if the program is entering in this second procedure here, or just part of this procedure, second step of the procedure, we are assuming that the constraint was not satisfied. So this gave false, basically, and it will enter here, backtracks, and it enters here. Now here we have the same thing, but what will change? It is this one, the output, and we have the recursion. So going further, to go further, we have to pass R, and we have to pass the OG. So just the list here, because this one, it was verified by this one that it's not possible to add R there. So just pass OG, and the one assigned, now it will return something. So we call it the rest groups. Basically, we can call it whatever we want. It's just the output. Now, which should be the output here? Now we don't want to lose this G. So G, it will be present here in the head, add it, and then we have the rest of groups, basically, which are these one here, which have been assigned blah blah blah, but we don't care, because even if you assign this rest, even for example, if R succeeded in the assignment part, this will be the return of these rest groups. So the rest groups, it will have these values here, which is in this case the R, it will be the value that was assigned to this one. The G, it is this one. OG, it is this one in our case. So here we have to put the rest of groups as output, final output, and then cover like this. And this is done. We are going through here with this one. We go through with assign all. We go through all these values one by one, and with this one, we go through all these ones, all these containers, let's say groups, one by one. So we have finished with this part. Now what we have to define is the constraint. Like, how can this procedure be modeled? Constraint is modeled as any other procedure. It has two values, basically. Let me see. Groups count elements. Yes, count elements here. Okay. Constraints, it will be also in this case, it has a base case, basically, which takes in input. Now, as we see here, it takes the input R and G. R is a value and G is a list. So it is R, which is a value, and then the list with the structure. We just get the head of the list. We call it generally the other region, and the tail of the list, which is, we call it rest of the regions, remain here. So these are now all values. The rest of the region is a list of values. It is like this, for example, with SA, Q, NSW, and so on and so forth. And OR is, for example, NT. And moving forward, we have defined this rule. This had a rule like this should be not. This is not neighbor, so R should not be neighbor with R. So these two regions, if R is a neighbor with R, and we will define neighbor that later on, it means that we cannot assign it to this group. If it's not, if this returns false, with this symbol here, it will be true. Basically, it transforms into true. It's like not this expression. You know something? I think we're gonna write it also not, and like this. They're equivalent. And we go further on checking other constraints, so all the other values of the list. And what we do is that we pass the same value of the same region, because this is our region that we are interested in, and the other values of the list to be checked are, and we finish. Now, which is the stopping condition of this one? This is not the bad case. This is this is the intermediate case. Intermediate case. The base case in this one is when we don't have any more values remained here. So basically, the base case could be written like this. This is an empty list, and this we can remove it completely because we don't care. But this is just a placeholder. So if we're saying if there are no values remained, please finish it. And it's finished. Now we have to define neighbors. Neighbors is again a procedure which is defined as with these facts here: adjacent of region with this or other region and other region, or adjacent of other region with region. We are basically just saying that check if these two regions are adjacent with each other. But we are checking, being that, as I said before, we are not basically putting both the Western Australia adjacent to Northern Territory and Northern Territory adjacent to Western Australia. We have to put it like this. We have to put adjacent region, which will be, for example, Western Australia, and the other region, which will be Northern Territory, and or, in case this is not verified, check the other part, Northern Territory before and Western Australia again. And it will be called here basically, and this is called the condition. This is the condition to be satisfied. And that's it. That's it. We just run it and see if it works. Solution. And what we have to see is that, as we see here, we can also put 10 solutions. As we see here, 28, what is called? Okay, just some errors. Don't know. Okay, if we see like this, we have 1000 values, but we can. So if we see, like in the first, what we are saying here is that in the first list, we have assigned the T, which is a territory, which will have the values. Each list has a value. Basically, the first list it will have red, the second list it will have green, and the third list it will have blue. Basically, this is the way that we have modeled the program. So, which will be the regions to which it will be assigned the value of red? It will be the T, the N and NSW, the Q, and Western Australia. And which will be the ones that will be assigned the value of green, the VU and the VU and NT, and so on and so forth. So this is one solution to the problem, and there are a lot of solutions. that we can have based on the constraints that we have here. We can also put a constraint, for example, saying that adjacent T is with Vo. We can say that, and we'll see that Vo and T will never be, for example, let's find where, okay, this one, for example. When T and Vo are within the red, so to both of them can be assigned red, now we will see that this will be removed. So we will not have Vo and T at the same list again. Just do 100 values, and you will see in all of these values we never have T and Vo within the same list. You'll see all of them. You can check all of them. Basically, because what we have said is that this is a constraint. This is now we are saying that T and Vo are adjacent to each other, so they cannot have the same value. So that's the whole idea behind it. You can also debug it and see the code step by step. Oh, it is entering the whole program. So it models here, and you will see all the results here. All the calls that computer performs. See you in the next video.